Alright, so today we're going to be talking about the atomic numbers, the atomic masses, and the atomic weights. First up, we're going to talk about the atomic number. And this is going to be equal to the number of protons. And this is unique, so every element has its own unique one. And AN is just short for atomic number. So if we go here to our periodic table, each of these elements has, a certain number of electrons. And right here, this integer at the top is telling us what our number of protons actually is. So hydrogen has 1 proton, helium has 2, lithium has 3, beryllium has 4, boron has 5, carbon 6, and so on. So each of these, and this is the whole reason the periodic table is arranged this way. It's arranged in order of increasing atomic number, increasing number of protons. Each one of these is unique. All right, so if you have here carbon is always going to have 6 protons. If it has 5 or 7, it is not going to be carbon. So, that's how you know what the actual atomic number is for this. Now, if we're dealing here with a neutral atom, then the number of protons is going to be equal to the number of electrons. Okay, so neutral atoms, number of protons, number of electrons. So remember, the proton has an equal and opposite charge to that of the electron. So if we want all of our charges to cancel out, we need to have the same number of protons and same number of electrons. All right, now an ion, and we're going to be talking more about these later on. In this case, an ion, this is going to be a charged particle. And in this case, since we're now dealing with something that's charged, the number of protons is not equal to the number of electrons. This is what we're going to be talking later on. Ions here are of different numbers of electrons to protons. And down here, an isotope. Okay, so this is an element with the same number of protons, but different number of neutrons. Okay. A very famous isotope that you may have heard of, uranium-235. So U-235 and U-238, so uranium-238. Another one, carbon-12 and carbon-14. Okay, so the uranium-235, this is the fissionable one. This is the one if you want to make an atomic weapon. This is what you need a lot of. Meanwhile, the uranium-238, you can't really make any atomic weapons from this. The physics isn't just right. So if you apply a neutron to it, it won't go boom. So in that case, that's why they always try to enhance the amount of uranium-235, because this naturally occurs at a very, very low concentration. Uranium-238 is the vast majority of this. So that's why I try to enrich the fuel, as they say. Carbon-12 is the vast majority of all the carbon that we have, in all of our cells and everything. This paper is 99% carbon-12. Carbon-14, if you've heard of carbon dating, this is the particular isotope of carbon that they use for that. And what's different between these, so remember uranium here, has a unique atomic number. So uranium is always going to be 92. So this is always going to have 92 protons. Carbon down here is always going to have 6 protons for this. But the number of neutrons is different. Now, these numbers here are not the number of neutrons. Okay, so this is the number of neutrons. These are what we call the mass numbers. Okay, so these numbers that I'm underlining here, these are the atomic mass number. And this is commonly just called A. And this is going to be equal to the number of protons plus the number of neutrons. Okay, so if I have here uranium-235, uranium-238, both of these have 92 protons. So my uranium-235, this is going to have 92 protons plus 143 neutrons, and my uranium-238 is going to have 92 protons, because it's the same thing, plus, so it's going to be 3 more, so that's 146 neutrons. And if you can see very easily, 92 plus 143 is 235, 92 plus 146 is 238. And similarly down here, my carbon-12, this is going to have 6 protons plus 6 neutrons. 6 plus 6 is 12. And here my carbon-14, that's going to be 6 protons, because it's still carbon, plus 8 neutrons. So the atomic number, that's very easy. If you know it's carbon, it's always going to be 6. Uranium's always going to be 92. Iron's always going to be 26. So, these are very easy to figure out if you know that. All right, so these atomic mass numbers here, these are always going to be nice integers, right? Because if you're just adding number of protons plus number of neutrons, then you are always going to have an integer number because you only have whole numbers of these things. Also, since these elements right here, if these are all neutral, so if all these things are neutral here, this is also would have 92 electrons, or 6 electrons, or 6 electrons. Okay, so if these are neutral atoms, they will have the same number of electrons as protons, same electrons as protons. If these were ions, which we're not going to deal with right now, these number of electrons can vary. So the number of electrons can vary, will still be the same element. The number of neutrons can vary, same element. Number of protons has to be the same because otherwise it's going to be a different element. So this was the atomic mass number. Now, what we can look at here is the atomic mass. So this right here is the actual mass of an isotope. So this is looking at the actual mass of the uranium-235, 238, carbon-12, or carbon-14. Okay. And here, just to show you what these numbers are, for the uranium-235, uranium-238, carbon-12, and carbon-14. So this is the isotopes themselves. And the actual masses of these are, for uranium-235, it's going to be 235.0439299. For uranium-238, it's 238.05078826. For carbon-12, this is by definition, we're going to see this later on, exactly 12.0000, and so on. And for carbon-14, that's 14.003241. And the units on these are AMUs. So the AMU, this is atomic mass unit, and 1 AMU is equal to 1.66054, and so on, times 10 to the minus 24 grams, or sometimes you could also write this as 1.66054 times 10 to the minus 27 kilograms. Okay, so that's just the atomic mass units for these. So as you can see right here, the atomic mass and the atomic mass number, which is up there, are really close to one another, right? So 235 and change, 238 and change, carbon-12 exactly on the button, and this is actually by definition. And carbon-14, it's 14 and change. So really the atomic mass, a number here, and the atomic mass are pretty close to one another. So a lot of times if you're just doing a quick little back of the envelope calculation, if you know what the actual atomic mass number is, at least to the integer, you're going to be pretty close to what the actual atomic mass really is. Now, how do we actually determine this? It's actually done using something known as a mass spectrometer. So if you happen to be watching any of those crime shows like CSI or Bones, and you hear them saying we're going to be putting the sample into the mass spec, that's what they're referring to. So what you do is you take one of these isotopes, you zap off an electron, and then you have a charged particle. You put that particle into a magnetic field, it bends it, and based upon the amount of bending, you can actually tell what the mass of this particular isotope is. There's actually more advanced techniques now, but that's the gist of it. And you can actually attain very, very high accuracy for these particular atomic masses right here. All right, so next up we're going to be looking at the atomic weight. But before we get into that, because we're going to be talking about weighted averages, we just want to understand what we mean by, an average, a weighted average. So first off, a normal average. So the normal average, what you normally do here is it's basically going to be you're adding up all your things here from I equals 1 to n, and then you're dividing by n. So what you would basically be doing in this case would be adding up, let's say I want to find out what the class average is for the exam grade. So then in that case I would be adding up all the exam grades and then dividing by how many students actually took the exam. And then that would be my class average for the exam. Okay, and that's the usual average. You just add up a bunch of things and then you divide by how many things you actually have. So that's the normal average. Here we're going to be looking at the weighted average. And in this case, we're going to be taking, again, we're summing this up from I equals 1 to n, But now we're going to have little weighting coefficients, a sub i's, multiplying it by our x sub i's, which is going to be our whatevers we're talking about. In this case, it's going to be the atomic masses. So these little weighting coefficients over here, for the regular average, all the a sub i's are exactly the same. All right, so if they're all exactly the same, they're all going to be the 1 over n. And that's just going to be your simple average. But in this case, when we're dealing with the weighting average, the weights are going to be slightly different. So how we know that if we actually did this right, we have a second thing we also have to work out here, is that if we sum up all of our weighting coefficients, this is going to be equal to 1. So that's, a constraint we have on our weighting coefficients, that they all have to add up to be exactly 1. And since we are dealing with real, things that we're not going to be dealing with any imaginary numbers or negative values, also the a sub i's are going to be greater than 0 as well. So we're not going to have any negative values in. And I can also put greater than or equal to 0, because you can definitely have equal to 0. If that's the case, well, then it just works out to be 0 in that case. All right, now this seems really complicated. Where would we actually use this? Well, think about if we're dealing with a class, and there's going to be several different things that you're graded on. So let's say you have here, a lab, you have quiz, you have homework, you have exams. So you have these three things, but you're not just going to take all the grades that you have and just add them up, because the exams are weighted more, right? They count for more of the grade. The homeworks don't count as much, quizzes don't count as much, labs maybe a little bit more because you want some practical lab experience. So what you're going to say here is, let's say the labs are going to be 15% of your grade, and then here your quizzes are going to be 10%. And then the exams over here could be 50%. And if I did my math right, that means my 0.15 plus 0.10 plus 0.25 plus 0.50, that's equal to 1. Exactly. And that's, if you've had this a lot of times in your classes, right? So this is essentially what we're doing here for a weighted average. So we're going to be looking at not just the actual values and just averaging it out, but basically seeing what proportion is actually around and coming off of this thing. Another thing that they do weighted averages for, if you look at the inflation rate. So, the inflation is the rate at which prices increase. So if you go shopping, like the price of milk, the price of vegetables, your price of your clothes, your price of your gas, all goes up and down. So if you're looking here at the inflation rate, basically, it's all these things that you're adding up. So you're gonna, and this is, your weighting coefficients here, but you're going to have certain amounts for, real estate, clothes, energy, food, computers, so it's and a bazillion other, subcategories that they actually look at. And, you just don't, average out how much, these prices actually increase. You start looking at how much these actually increase, and you weight them with different weighting percentages based upon, how much impact they have in the actual economy. So that's basically what, some more examples of the weighting average. So now we know what the weighting average is, we can look at the atomic weights. Okay, so the atomic weight is, all right, so the atomic weight is the weighted average of the atomic masses of the isotopes of an element. And the way we would write this out is that the atomic weight is equal to the sum, and it depends on how many we're doing here, of the abundances times the atomic masses. And this is atomic mass, not the atomic mass number. So in other words, we're going to be using these values right here, not these values. And also the additional constraint is that the sum of all my abundances is equal to 1. And again, all my abundances here, these are going to be somewhere between 0 and 1. Okay, so we're not, even though we're going to be dealing with percents, remember a percent, you move the decimal point over by 2 places to get into decimal form. So let's do an example here. Let's say we have iron 54, and this has its atomic mass of 53.940, and this has an abundance of 5.82%. The iron 56 has an abundance of 55.93, or a weight of, or mass of 90.935, and this is 91.66%. The iron 57 is 56.935, and that's going to be 2.14. And the iron 58 is 57.933, and that's 0.33%. Okay, so all of these units on this are AMUs, and this, of course, is my abundance. And this, of course, is atomic masses right here. Okay, so that's the atomic masses in AMUs for all of this, and this is my abundances in percent. So if we want to calculate this out, what we do is we take this, multiply it by that, add it to this times this, add it to that times that, add it to this times this. And again, since these are percents, remember to move the decimal point over by 2. So I'll just write out the entire equation here. So that's what I did, and just notice right here, all these percents, I moved the decimal point over by 2 spaces. So now, of course, if we add all these things up, this plus this plus this plus this, that's going to give us our, well, the abundance is here. If you add them up, it equals 100% because that's what it should be. Also, well, we'll just do this calculation right here and figure out what the atomic weight of that actually is. So if we do this calculation here, we get 55.82. At least to the correct number of sig figs, although actually this has only 2 sig figs down here, but we'll just go to 4. 0.82 AMU for my atomic weight. Now if we look here at the value here, and this, of course, this is my atomic weight right there. If we look at this value here, notice that it is between the biggest and the smallest values that we actually have. And that's also the other thing, if we're talking about averages over here, the average is always going to be between the biggest and the smallest value. Same thing here for the weighted average. It's always going to be between the biggest and the smallest value. So if we have over here, my atomic weight is 55.82, then this is going to be between my smallest, which is 53, and my biggest, which is almost 58. That's in the middle. That's good, right? Also, if we look here at the weightings, most of this is coming from the iron 56 isotope. So it should be closest to this 55.9, and that's actually what we see. It's pretty darn close to this. The heavier isotopes don't impact it as much, and the lighter isotope, it goes just a little bit towards that way. So this is going to give us our atomic weight. So that's the important thing we just want to get away from this, is that if you look here, the smallest atomic mass is going to be less than the atomic weight, which is going to be less than the largest atomic mass. Okay, so the atomic weight is always going to be in between these two values. If it's not, you goofed up. And the most common way of goofing this up is forgetting, when we have here percents, to move the little decimal point over by 2 spaces. All right, and then as for the atomic weights, this is what is actually on the periodic table itself. So the individual atomic masses for each individual isotope, these values right here aren't actually on the periodic table, but the actual atomic weights are. And this is important because this is when we're looking at an actual sample of iron. So if you go pull up some iron out of the ground, or iron that's in a car or whatever, this is going to have this particular ratio of all of the isotopes. All right, unless you do some enhancing in there, it's going to have that particular ratio. So that's when you calculate this, and well, in this case on this periodic table it's 55.8. We calculate it to be 55.82. That's 845. So it's a little bit different. The reason is probably just I just copied this out of the book, so it might be a little bit different than the source that made up this periodic table. But either way, just use the values that are on your periodic table, and you'll be happy. Now, one little thing that you just have to pay attention to here is the artificial elements. So you notice right here, like technetium and everything after bismuth over here, all of these things, all these down here where we have the atomic weights, these are all, except for a couple of things right around here, all of these have parentheses around them. And the reason we have these parentheses around there is, unlike the naturally occurring isotopes where they have very well-defined abundances, and we can go and measure this very easily, since these things are created artificially, they do not have one set abundance. So you can like tune your reaction and actually cause a different abundances or different isotopes to actually be formed, and that's going to change it. So this is the generally occurring ones, the longer lived ones, but it's just as a guideline to tell you, approximately what the mass is, but, since we don't know what the actual atomic weights are because the abundances can vary so dramatically, we don't report them. So that's why, it's like even over here, technetium, says 98, but you could very easily have 99 or 100 technetium. It just depends on what reaction you actually undertake. All right, now as for the symbols that we're going to be using here, so if I have here, the basic thing is here the A, Z, and then some symbol like this. All right, so here, and this can also be equivalently represented as symbol dash A, or just the symbol as in the name. That's why MBOL. So it could equivalently be represented as one of these three things, and that's how we we'll see it many times there. So here, the Z is equal to the number of protons. All right, and then this, of course, is just, your atomic number. Symbol, that's just going to be, the name of your element. And really, if we think about it, the Z here, since that's the atomic number, and if we know the symbol, we know what the atomic number is already. So this right up here is just redundant. So like we were talking about earlier, if I have here carbon, I know it has 6 protons, because if it doesn't have 6 protons, it's not carbon. If I have here my uranium, it has 92 protons. If it has anything else, it's not uranium. So if we just put in here just the symbol and leave off the Z, we know what that is automatically because it simply cannot be anything else. And then down here, A is equal to the atomic mass number. And this is equal to the number of protons plus the number of neutrons. And that's just exactly like what we were talking about earlier, that these numbers right here do not represent the number of protons, or the number of neutrons, but this represents protons plus neutrons. So we just have to be very careful about that. And here, the Z and, I want to use there, and A, these are both going to be integers. All right, so these are just going to be whole numbers. All right, so we can do a little example here just to test our knowledge. So let's say I have here boron 11, like this. And by the way, this could equivalently be written as just 11 boron, because that 5 is redundant. Because here, since boron is always going to be have 5 neutrons, or sorry, since boron is always going to have 5 protons, we know that this is always going to be 5. So I don't have to write that 5 down there. It's redundant information. So, if you happen to see the boron without the 5 down there, you know why. It's because if you just have to look on the periodic table and you will know exactly how many protons it actually has. And we could just easily write this as boron 11 or boron 11. So either way, they're all equivalent examples of that. All right, so let's say I have here my boron 11, and I want to figure out, well, what is my Z, my A, my number of protons, my number of neutrons, and the number of electrons that I actually have in there. So here we have the 5 written right on there, so that's going to be 5 for my Z. And Z, that's the same as my number of protons. That's my atomic number, so that's no problem. My A, that's just going to be my 11. And then we're just going to go through here and say that's my number of neutrons. Remember, that's going to be 11 minus the 5. So this is going to be equal to 6. And since we're dealing here with a neutral atom, that is going to have the same number of electrons as protons. So this is going to be 5. All right, let's say I have here a Z of 9, and my number of neutrons is 10. So what element is that going to be? Well, here Z is going to be the same as my protons again, so that's going to be 9. We're 9 plus 10, so that's going to be 19. That's going to be 19, 9. Then we just have to look which element that is. And here it is. That's going to be your fluorine. Next up here, let's say I have 31 and 15. Well, here, if I have 15, that's going to be 9 over, or sorry, this is going to be 15 as well. My number of neutrons, that's going to be 31 minus 15, so that's going to be 16. And then my number of electrons, again, since this is neutral, that's going to be the same as my number of protons, which is 15. So here, this is going to be 31, 15. Got a periodic table, and that's going to be phosphorus. And one little final example here, let's say I have 28 protons and 31 neutrons. Well, 28 plus 31, that's going to be 59. And my Z, that's also going to be 28. Again, since we're neutral, that's also going to be 28 for my number of electrons. So that's going to be 59, 28. And which element is 28? That's nickel. All right, now if these things weren't neutral by themselves, so if we were dealing with charged ions, which we'll look at later, the charge is equal to the number of protons minus the number of electrons. Now, how do we know this? Remember, protons are positively charged, electrons are negatively charged. So that's why you're putting the subtraction here. So if I have more protons than electrons, it's going to be positively charged. If I have more electrons than protons, it's going to be negatively charged. In all these cases, these were neutral, so they have the same number of protons as neutrons, protons as electrons. But if we're dealing with charged ions, then we would subtract the number of protons from the number of electrons to tell the charge on that particular ion. All right, so stop that there.